So the next reaction mechanism I'm going to talk about is nucleophilic substitution using cyanide ions. So we're going to take again our halogenoalkane, our RX, we're going to react that with some potassium cyanide, and that's going to give us something called a nitrile. So the potassium cyanide is KCN, and what that's going to do is that is going to dissociate into positively charged potassium ions, and we're also going to get some of this. This is our cyanide ion, and this is our source of electrons, so this is our nucleophile. And notice that the negative charge is on the carbon, so this is where your lone pair is coming from. Okay, it's not coming from the nitrogen, it's coming from the carbon. So again, if we take the example, we'll do bromoethane again. If we have our potassium cyanide, so there's going to be some potassium in here, and there's also going to be some of our cyanide. If we draw our lone pair of electrons in, so we know where it's coming from, I'm going to put in the delta positive and delta negative charges, delta positive carbon, delta negative bromine. I'm going to draw our arrow from the electrons to the carbon, and then from this bond to the bromine. And the result of that is going to be this. So this is what we would call propane nitrile. Okay, so if we've got bromoethane, this is propane nitrile. So we've actually added an extra carbon atom onto the chain. Okay, and we call this ascending the homologous series. So we're adding an extra carbon atom, which is why these reactions are quite useful. So the conditions for this reaction, this is going to be warm. So this is not boiled. This is warm. Again, we're going to reflux it to make sure we're not losing any of our products. This is going to be done in an ethanolic solution. So it's not in water, not like the previous one. So the solvent is ethanol, and we're going to need some potassium cyanide as our source of the cyanide ions.